Okay, this is I thought this was a very straightforward question myself, and I didn't really understand. There's a lot of people didn't seem to read it, I guess, but let's quickly take a look at it. Calculate the change in gravitational potential energy of the stone as a result of falling through 16 meters. So it really just wants us to do GPE. That's a GCSE question. GPE, MGH. We know the height is 16. We know gravity, of course. We know the mass, 56 grams. A lot of people don't know the difference between grams and kilograms, but I'll tell you, there's 1,000 grams in a kilogram, so there's 56 times 10 to the minus 3 times by, I've not left enough space, and I'm going to put my 9.81 on the end. 9.81. That's going to give you a value. I'm even going to do it for you. What is that value? The value is something like 8.78, so roughly 8.8 joules. Okay, and then it wants you to calculate the total kinetic energy of the stone as it reaches sitting. And looking down here, it's a 3-mark question. It's not going to be just calculate the kinetic energy. So we know the kinetic energy there is going to be is given by the 18. So what at this stage it's got kinetic energy. When it gets to here, it's going to have this kinetic energy, and this GPE will have turned into kinetic energy as well. So we've got to get the whole lot together. Okay, so in a way we could say KE at the sea level, C is equal to KE at the cliff, the top of the cliff, plus the GPE. And that's really what it's asking us to do. So for this one, you do a half times the mass again, 56 grams times 10 to the minus 3 times by velocity squared, which is 18 squared. That's a GPE, sorry, the KE at the top of the cliff, plus this value found there, 8.8, and that'll tell you what you need to do for that. So I'll let you work that out. Once you've got this value here, you want to show that the speed of the stone, it's using this value here to show the speed of the stone is approximately 25. So you will know your total KE from there, that'll be this value in here, and that's going to be equal to a half times by mv squared. So the velocity will be 2 times the KE divided by m square rooted, and it should come out to close to 25. C, calculate, no, it doesn't say calculate, it says state the horizontal velocity of the stone as it hits the water. Well, the assumption we always make for these types of calculations is that there's constant acceleration in one direction vertically and constant velocity in another direction horizontally. So if it's 18 meters per second there, you've guessed it, it's going to be 18 meters per second there. And this word state as opposed to calculate is a big clue. Make sure you pay attention to it. On the grid, it wants you to draw a vector diagram to represent the horizontal velocity and the resultant velocity of the stone as it hits the water. So you can use your own scale, but we know that it's got a horizontal velocity of 18 and a resultant velocity of roughly 25. Okay, so using whatever scale you want, I'm just going to use it down here. 1, 2, 4, 6, 8, 10, 12, 14, 16, 18. Excuse me, you don't want to waste your time watching me count out the things, so I'm just going to do it smaller than I should for the sake of speed. Obviously you double it or whatever, and you know that this length here, okay, is total is 25. So you could get a ruler if you wanted to work out. You don't even have to count the squares. You could just basically make a line there. Maybe I don't know if that's 18 centimeters, but 18 centimeters. Let's say you can get 18 centimeters in there. I suppose maybe make it 9 centimeters, and then one in there, which would be 12.5 centimeters. So decide a scale, but I'm going to very quickly approximate that. If that is 18, and I've got a scale which I'm not bothering to measure, but if that was 18, that would be 25. Okay, of course, that is the direction of that one, that's the direction of that one. Of course, this would be the vertical velocity when it hits the water. Again, if I was you, I'd make it bigger, but it's only a 1 mark question, it should be fairly straightforward. Finally, use your vector diagram to determine the angle with the horizontal at which the stone hits the water. So you're going to try and calculate this angle here. This is the adjacent, this is the hypotenuse. Sine theta equals cos theta equals adjacent over hypotenuse. So that would be 18 over 25. When it says use the vector diagram, they probably really want you to use a protractor to show a protractor, but I don't have one with me. So you'd get an angle, whatever that is. Again, I'll let you work that out. Okie dokie.